Hey guys, so this week we are talking about igneous rocks. And so we're going to work on distinguishing igneous rocks and understanding how they form. And we're going to work on how we classify and identify igneous rocks in the lab. So remember from last week's lecture that we can break rocks down into three main categories: igneous, sedimentary, and metamorphic. And so the next couple of weeks in class, we'll be talking in depth about each of those three categories. And this week just so happens to be igneous. So igneous rocks are formed from molten rock material. So before we start talking about how we classify igneous rocks, we need to talk a little bit about molten rock. So molten or melted rock consists of liquid, gas, and solid crystals. So sometimes I think it's easy to think of magma or lava being just a liquid, but it's important to know that not only do we have that liquid melted component of molten rock, but we also have some gases dissolved or trapped in that melted material. And we also have minerals that have already crystallized within that liquid material. So think more of magma and lava as being kind of like a sludge or a mixture of materials and not completely a liquid. And so to distinguish molten rock, we call it magma when it is below Earth's surface, and we call it lava when it is at or on Earth's surface. Right? So we talk about magma chambers when we talk about volcanoes, but we talk about lava flows when we talk about that molten material on the surface. And so different types of molten rock have different compositions, different minerals, different temperatures, and different viscosities. And so we classify our magmas based on what their compositions are, what minerals make them up, what temperature they're at, and what their viscosity is. And then those magma compositions are related to the igneous rocks that we end up getting when this magma cools. And so we've probably heard the word viscosity before because we talk about oil viscosity in cars and those types of things. But viscosity is the tendency within a body to resist flow, which is just a really fancy way to say how sticky a liquid or a fluid is, right? So viscosity is just telling us how sticky a liquid is. And if you have a lower viscosity, you have a runnier fluid, you have a fluid that is less likely to resist flow. So in this example, let's think of water as being something that has a relatively low viscosity. A fluid that would have a relatively higher viscosity would be like honey or syrup or molasses, right? So some syrupy substance would be something with a high viscosity, right? Because within that fluid body, there's more resistance to flow. It's going to flow more slowly, right? Kind of flows more in a chunk, right? Toothpaste is very viscous, but viscosity is important when we're talking about magma. And in class, when we're face-to-face, we will talk about an example of viscosity, and I can bring up a short video to show you visually what differences in viscosity look like. So, right, we care about molten rock because igneous rocks form from the cooling and solidification of molten rock. And so that's kind of why we start with igneous rocks in this class is, right, we've talked about how minerals form and what minerals are. And now we're going to talk about rocks, which are made up from minerals. And of our three different types of rocks, it kind of makes sense to start with igneous rocks because they form sort of brand new from cooling and solidification of molten material. And so we can categorize igneous rocks in many different ways. And so one way that we can categorize them is based on their chemistry, right? So we can talk about what makes the rock up. And then we can also categorize igneous rocks based on how they form. So whether they form inside the earth or at the Earth's surface, right? So this is kind of going back to those words, why we classify magma and lava as two different things. It's related to that the formation mechanism of igneous rocks and the type of igneous rock you get out of that environment depends on whether that magma cooled underground or at the surface. So those are kind of the two things that we use to classify or categorize igneous rocks. We use chemistry, so what they're physically made up of, and how they formed. And in the lab, we see those two things as the color of the rock, which the color is directly related to the minerals that make the rock up, or the chemistry of that rock. And we use something called texture, which is related to the mechanism through which that igneous rock formed. So in the lab, we use color and texture to base our categorizations off, right? To identify igneous rocks, we use color and texture. And that's because those two things represent chemistry and how the rock formed. And if we're thinking about how igneous rocks are classified based on chemistry, we have to think back to the chemistry of that molten material, right? So whether it was magma or lava. And so when we talk about volcanoes, we'll talk about this a little more, but when we have igneous rocks with relatively low density and that are what we call of felsic chemistry, then those come from really high viscosity magmas, right? So we're going to hear this about 6 million times, so it's okay if this doesn't make sense yet. But no, we have something called felsic chemistry or felsic minerals, and our felsic minerals make really high viscosity magmas, right? So felsic magma has really high viscosity. Because it has really high viscosity, it's very sticky. The gas can't escape, and so we get very explosive eruptions. On the other end of the spectrum, if we have a mafic chemistry, so a molten rock made up of what we call mafic minerals, that typically has a lower viscosity, so we have a more runny magma, and then we're less likely to have explosive eruptions. And so later in this lecture, we'll have definitions for felsic and mafic, but no, as we're classifying igneous rocks, we can classify them based on their chemistry, their temperature, their viscosity, and all those things help us identify or classify igneous rocks. So that composition or the chemistry, which listed in this table as type, has a control on the density, the temperature, and the viscosity of that molten material. And so that type is related directly to the chemistry. We sort of use chemistry and minerals interchangeably, right? Because the chemistry, the elements that make up the molten material are the building blocks to make the different minerals that we then see solidified in our igneous rock. All right, so we can think about these things, this classification, on a scale. And so again, we can see as we look at composition on a scale, notice that composition, we have multiple igneous rocks listed under each one of these compositions, which means that first we look at the composition of the rock, which in the lab is what color we see that rock to be. right? So we see rock composition. And then if it was an intrusive rock that formed underground, we get a texture called coarse-grained, which creates one type of rock. And if it formed above ground, we get something called fine-grained, and we get a different rock name. So notice that we use both composition or color and the formation mechanism or the texture to identify our rocks, right? The percentage of minerals in each of these varies based on composition. And then we can also see that as temperature increases, viscosity decreases. Again, we will talk about a lot of those relationships again when we talk about volcanoes in a couple weeks. So right now we're really focusing on really these basics of we have molten material. It has a certain composition, right, which varies along some scale. And that molten material can either cool underground or above ground, and those two things can help us classify and determine what igneous rock forms. So when we're classifying igneous rocks, again, remember that texture is an indication of how that rock formed. So in this sense, texture refers to the size, shape, and arrangement of the mineral grains that are making up our igneous rock. And this texture, right, how the minerals are arranged, how big they are, the shape of them, tells us how that rock formed. So specifically, we have intrusive igneous rocks, which form when magma underground or inside of a volcano cools. When magma cools underground, it has a really long time to cool, right? Because the temperature isn't changing very quickly, right? It's kind of sheltered. It's got a little bit of a blanket where the temperature underground is closer to that of a magma chamber temperature than the temperature at the surface. And sometimes that magma kind of rises very slowly towards the surface. And so you have a much slower temperature change underground than you would at the Earth's surface. And so because this magma is cooling underground, it just has plenty of time to just kind of hang out and cool off slowly. There's lots of time for minerals to form large crystals. So in our intrusive igneous rocks, we get large crystals. On the other hand, when we have extrusive igneous rocks, these form when we have lava that cools at the Earth's surface. And because this molten, very hot rock material is hitting the air very quickly, it undergoes something called quenching, where it cools super quickly, right? So if you've ever watched videos of volcanic eruptions, you'll have noticed how quickly that lava starts to get a crust on the top, right? And so it cools very quickly, right? So it's important to know, in the grand scheme of things, you might think, well, it's maybe not an instantaneous thing, right? It may take months for lava to cool all the way at the Earth's surface. But in the grand scheme of the Earth's history, of geologic time, that is like an instant. So our extrusive igneous rocks are cooling very quickly. And because they cool so quickly, there's not any time for minerals to form, or if there is time for minerals to form, they only form really small crystals. So extrusive igneous rocks at the Earth's surface, they get quenched, right? They cool very quickly, so you get no minerals, or you get very small crystals, think ones that you can't see with your naked eye, right? You need a microscope to see these crystals. Intrusive igneous rocks that form underground have a lot longer to cool, and so they're able to form large crystals. So in the lab, we can identify intrusive and extrusive igneous rocks based on their texture, right? Based on how big those crystals are. All right, here's our felsic and mafic silicate minerals, right? So we have our texture related to intrusive versus extrusive environments. Now let's talk about composition. So with our magmas and our molten materials, we sort of have two main compositions, two main chemistries of our magmas. And the first one is called felsic. And so our felsic silicate minerals or our felsic silicate magmas have a lot of silicon, which is silicon oxygen, and they have a lot of aluminum. They have lesser amounts of iron and magnesium. Right? So the important thing to know about felsic silicate minerals is that they have a lot of silicon and aluminum. Some examples of minerals, right, which we will have looked at in the lab this week, are quartz and feldspars, right? So remember back to what quartz and feldspar looked like. Felsic minerals are typically lighter colored, right? These are usually our white, clear, pink, bluish minerals because they're higher in silica and aluminum, which are lighter in color. Typically, they're less dense and they crystallize at lower temperatures. So as we look at igneous rocks this week, keep in mind that granite is a very common felsic silicate composition igneous rock, right? So granite, think granite countertops, think about how they're usually pinkish or white because they are felsic. Our continents are largely made up of felsic silicate minerals. So on the other hand, on the other side of that coin are mafic silicate minerals. So mafic silicates are richer in iron and magnesium, and they have less silicon and aluminum. So felsic, high in silica and aluminum, mafic, high in iron and magnesium. Because they're higher in this iron and magnesium, they typically are darker in color. So some minerals that we've talked about, olivine, amphibole, pyroxene, all of those darker colored minerals are ones that are mafic. So again, typically are darker colored guys, they're more dense, and they typically crystallize at higher temperatures. That'll become important when we start talking about types of volcanoes and how magma composition, whether it's felsic or mafic, is related to the type of volcano that forms. For now, just know mafic are our darker colored minerals, felsic are our lighter colored minerals. We commonly have mafic minerals in our oceanic crust. So largely our ocean basins are made up of mafic minerals, and our continents are made up of felsic minerals. So we will use these words a lot throughout the beginning of the semester. So no, felsic, lighter colored, richer in silicon and aluminum, mafic, darker colored, richer in iron and magnesium. So here's just some pictures because I say light and dark colored, and then we get into the lab and I always joke, like, geologists are in the field and we always see like gray and brown rocks. And so we get really excited when something is like not those two colors. So these next couple slides kind of walk you through the identification process that we will do in lab for igneous rocks. So here are two felsic igneous rocks. Notice they're both light in color with whites and pinks, right? There is still some black in here, right? So there's a black mineral in both of those. But overall, if you kind of squint and stand back, notice that largely this is lighter in color, pinky, salmony color. On this side, we have granite, And you notice you can see each of those individual crystals because we have big crystals that have formed in an underground or an intrusive environment. On the other side, we have small crystals in our rhyolite, right? So here we have an extrusive example of an igneous rock. So these two igneous rocks have the same composition. They're both felsic, but depending on where they formed, we call them something different. In between felsic and mafic, we have a class called intermediate, right? So it's somewhere in between the composition of felsic and mafic. These are commonly, I would say these look almost more like gray, right? They're somewhere in the middle between the lighter and the darker colors. In the lab, they kind of present as grayish colors or white and black speckled things. So diorite is our coarse-grained, big crystal, intermediate igneous rock. And andesite is our fine-grained, small crystal, extrusive igneous rocks. Here's mafic. Notice that as we move farther and farther along, things get darker in color. Again, we have our coarse-grained one over here, gabbro, and our fine-grained one over here, basalt. Notice this basalt has a lot of green in it, which you might not necessarily think of as a dark color. Olivine is an olive green mineral, and it always throws everyone off. Whenever you see olive green, think of that as mafic. Even though it's lighter colored, it crystallizes at the temperatures and has a similar composition to mafic. And then we can get to another class called ultramafic, right, which would be like super mafic, super iron heavy. We typically don't look at these in lab because they're relatively rare in the grand scheme of things. All right, so as we mentioned, cooling rate influences the texture of igneous rocks. So how deep they cool is a factor, right? So the closer you are to the surface, the faster you're going to cool. If you're really down deep in the earth, it's going to take you a really long time to cool because it takes longer for heat to escape towards the surface. The closer you are to the surface, the faster heat can escape. All right, and again, igneous texture tells us about the size, shape, and arrangement of the mineral grains within that rock. And those textures tell us important things about how that rock formed. And so we have 5 main igneous textures, and I've kind of hinted at them right through the rest of this, through the beginning part of this lecture when we talked about this one has big crystals, this one has small crystals. Well, there's actually fancy words for them, and we'll walk through and talk about each one of these in turn. So glassy texture occurs in extrusive igneous rocks where rock cools very rapidly, like so fast that there's no time for the atoms to arrange themselves into any regular order, right? So in volcanic glass and anything with a glassy texture, it just cooled so quickly, there was no time for any minerals to form, right? No crystals are in our glassy igneous rocks because they just cooled so fast there wasn't time for them to form that structure, that bond structure between the atoms. Glass, like real glass, you know, like window pane glass, forms through the same process where it cools so quickly there's no time for those bonds to form. That's why if you ever look at old buildings, you know, like that have original windows, you can tell that the glass has like moved and settled down towards the bottom of the window pane over time because it doesn't have any bonds in it. The fancy name for that rapid cooling is quenching. And we typically get glassy texture like on the top of lava flows. So if anybody's ever been to Hawaii, right, as the lava flows cool on top, we get this glassy texture. Can also be extruded from volcanoes during explosive eruptions. And in the lab, we'll notice we actually have kind of a smooth glassy texture and a frothy glassy texture, where if you've ever seen like a pumice stone, that would be something with a glassy texture as well. So glassy, it's named glassy because it's shiny, but it doesn't necessarily have to be shiny to be considered this texture. It all has to do with the fact that there's no crystals there. The next texture is aphanitic, which is when we have those really fine-grained rocks. So aphanitic texture is related to extrusive volcanic activity, where minerals form, but the lava cooled so quickly that those mineral crystals are so small you have to use a microscope to see them. So when we just look at them in the lab, you can't really see any shiny bits. Again, aphanitic texture comes from rapid cooling. On the other side of the coin is phaneritic texture, which is those coarse-grained rocks with really big crystals, right? So the ones that form intrusively underground that had a lot of time to cool, we call those phaneritic, which are crystals that are big enough to be seen with the naked eye, right? So you don't need a microscope to see the crystals. And then they interlock and form a tight mass or rock, right? So again, granite, right? All the crystals you can see in your granite countertops are an example of phaneritic texture. Remember that large crystals are related to relatively slow cooling rates. We also have a fancy texture called porphyritic, which is when we have both coarse and fine-grained minerals in the same rock. These are the result of some more complex formation mechanism where perhaps it started cooling underground and you formed some minerals that cool at higher temperatures underground, right? That solidify at higher temperatures. They solidified, and then maybe this magma was erupted and the rest of the rock cooled very quickly. So you have both big crystals and small crystals. And so, right, this is complex. The rock started to cool slowly and then erupted and finished cooling. And then finally, we have something called pyroclastic texture, which is when we get a bunch of things blown out of a volcano related to ash, and then that ash solidifies into a rock. And that's what we call pyroclastic texture. And so this material, the stuff that gets blown out of a volcano, we call pyroclastic material, and when that material accumulates, either through ashfall or flow, it forms into an igneous rock with pyroclastic texture. So we will talk about this obviously in class. We'll go over some of the important parts. Next week, we will practice identifying igneous rocks in lab. And so be sure you do your lecture assignment number 2. Let me know, summarize the lecture, and then let me know 3 things that you still need clarified or gone over again.